So if we were still talking like the r and theta are just over plane, that we have a height.
Exactly. So this would be just like the regions we draw. And then the actual function is going to be up here, down there. If I put a 1 there, of course, I would end up getting the area of that sector, right? Same ideas apply, and I know some of you guys are like, no, they don't, man. It's r and theta, there's extra shit there. But it's the exact same idea, just using different coordinates to get somewhere. Now, what would be why the shit would we do this? We just had a whole section that seemed to work perfectly. Yeah, so let's do an example here. Let me see what I got. I've got a couple examples here. Blah, blah, blah. Let me do this one. All right. You guys try to sketch this. Let me write the function here first. Notice it's xy. I don't care. Negative up there. Oop. This is 15.3. This is the double integrals over polar. So just take a minute and try to, don't worry about the function at the moment. That's going to be what pops into our integral. Just try to sketch that region. I know I'm currently in rectangular, but of course a big part of this section is going to be converting from rectangular to polar. Yeah.
What section are you trying to get to when you take the test?
Oh, we'll find out. We'll find out this Wednesday. Okay. Yeah. So if you didn't hear, the test been moved to next Wednesday, right? This on the 3rd now.
Yeah.
So we have one more day to try to get through what we can. I might as well tell you right now while I'm thinking about it. I decided go ahead and make 15.4 extra credit. And I already had made, what was the other section?
14.8.
14.8, yeah. Which kind of brings a tear to my eye, but 14.8, the math isn't really that difficult. I know you guys are like, I don't believe you, man. You have set me up this whole semester. I don't believe anything coming out of your mouth. All right, I don't know. But I got a few people who tried it out. It's really not that bad. If you're going into engineering, if you're going into physics, you probably want to look it through. But normally when you hit that, the reason that I'm okay letting it go is it is relatively simple math-wise. The concept's a little bit interesting, but if you read through it, it actually kind of makes sense. And whatever you do it in later, they're going to assume basically that you might not have ever seen it before. So they're going to kind of start from fresh. But even then, I want to get a little preview if you're going to go into those fields. 15.4 is really just applications of this. So they actually pretty much work it out to the point where you just got to plug stuff in and work it out. So still, it's just going to be, do you know how to integrate this stuff? So it's good for extra practices of integration.
So it's supposed to be double integrals f r theta dA, right?
So again, sorry?
It's supposed to be double integral f function of r and theta dA, right?
Yeah, so this here is our dA for polar.
And
Yeah.
they just differentiated this part, right? 1/2 r.
Yeah, yeah. That one's almost too hand wavy, but yeah. Once you see that, if you take the derivative of this, you get. Well, you got to be careful. With respect to what?
So r. So r.
But then, where would the d theta come from? You're assuming theta. So where would d theta come from? So it doesn't quite match up, right? But I like the attempt because it does make sense to be dA. Right? All right. So what is this? What does this look like? Be really careful. People are really optimistic about radii too much. What is the radius of that circle? Rad 2. So it's going to be, for this problem, it's going to be, so this region from, it's going to be in this circle that goes out to rad 2, but it's also got to be under this line, right? Now I picked a nice line. That's a nice line. That line goes at a what angle? 45 degree. Right? Y equals x is 45 degree angle, which is really important when we're going to transfer. Do you see why I might want to? You can try to set up the integral right now. So it's going to be, this is the region we're talking about down there, right? That's the region we're talking about. And we want to integrate that function over this region. So if you try to set up in rectangular coordinates, quickly see why you might not want to do that. And it's just screaming at you. There's two things that you consider to see if maybe polar is better. You got a function you're working with that's got a part that is screaming, hey. And then the same idea here, your region you're going over itself is circular. So there's two things that are kind of telling you, hey, you may be tripolar, right? So what's going to happen to how do I describe my region using polar coordinates now? That's where you got to be a little careful. Let's see. I do it this correct. What's the angle doing? Where's it going from to? This is where you got to be really careful. Yeah, if you said pi over 4 to 5 pi over 4, what's wrong with that? You would get the upper part, right? So it's got to go from this angle to that angle. So and then I'd rather just use negative, right? So it'd be negative. I got to pass that. I got to go all the way back here. Negative 3 pi over 4 to pi over 4. So theta is going to go from negative 3 pi over 4 to pi over 4. And what's r going to go from to? So as theta sweeps out, what's my r going to do? R is going to start at 0 and go out to square root of 2. Exactly. Yeah. Sure. So really, it's all about, they're going to give you a lot of problems with rectangular coordinates first. You graph it with that, you step back, you look at it, and you start to rewrite things in terms of polar. The mistakes people make are simple things like picking the wrong angles to go from to. You got to make sure you actually get the region that you want. Letting r go from negative rad 2 to rad 2. No, it doesn't, right? Very infrequently will r go below 0. Right? So that's...
Is it possible for some function if you do the wrong thing, the symmetry of the height?
It's possible. It's possible, but like we said, don't bank on it for sure, right? This has got symmetry to it, but of course it all depends on... If this was symmetric to the y equals x line above it, do you see what I'm saying? Then you would be golden. But that's a big assumption to make, and why would I take time checking that out? You know what I mean? Let me see if it is symmetric. No, screw that. I don't know if anybody would be able to prove that even, to be honest. Anyway. So let's see. What goes in here? Yeah, and what's it going to be now?
R squared.
And then, of course, so obviously this is a huge place people make a mistake. They forget that R. And that R very often saves your ass like it does right now. I need you to realize that as we get used to ideas, we start off with the intervals that work. You, of course, understand that, I mean, this was developed so that I could use what procedure? U sub, right? Because R squared has the derivative as R, but what goes here?
0 to 5.
Rad 2, that's dr is the inner one. And then theta, of course, goes from pi over 4. I like it. I like it. So go ahead and do that. Yeah, totally. That's why I shaded below that. That's y equals x. Y less than or equal to that. Yeah. And of course, y equals x is I don't have to do any work. The ratio would be 1, but it's a 45 degree. If it was y equals rad 3x, then I would have to think for a second about what angle is that related to. Yeah. Just in case you get done with this one, I'm going to do that one next. Change that into polar. So just to catch up with you guys, if you do u sub, du would be 2r, right? This whole thing be. So then I have to do this kind of thing. Right? So when you integrate, the inside, you would end up with 1 over u squared. And the integral of that is going to be negative 1 over u. I like it. So you end up with negative 1 over r squared plus 1. Evaluated from
0 to 0.
Stick with the marker that's working. All right.
The other one there.
Oh yeah, 1/2. Thank you. So then you get negative 1 over 3 plus 1, looks like, right? So the integral, so negative 1/3 plus 1 is going 2/3, so I get 1/2 of that, I get 1/3. All right, let me do it. Is everybody cool with that? It's going to be, rad 2 squared is 2 plus 1 is 3. That's negative 1/3 minus negative, so plus 1. Negative 1/3 plus 1 is 2/3. Half of 2/3 is 1/3. From negative 3 pi over 4 to pi over 4 d theta. It's awesome when you have a constant in there. It's 1/3 the difference between these two, and since that's negative, that'll be 1/3 the sum. So it'll be, oh, that's nice. Even better than I thought. Let's see. So it's just pi over 3. Cool. This will be pi over 4 minus negative, so plus 3 pi over 4 is 4 pi over 4 is pi times 1/3. Cool. I like it. So I'll do that a little quickly because that's 180 shit. Now this one I like because the inside function is not just x squared plus y squared. it's going to have some theta involvement. So, I mean, the very first step there is to try to sketch it out. So go ahead and try to sketch that out. Try to change it into polar. You can work with each other if you want to.
So the first step would be polar?
Yeah, sketch the region and then convert to polar so you can figure out your limits. Converting the inner function of polar is the easy part. Notice that when x, this is x here, right? When x is 0, y goes from 0 to 1. And notice that when x is 1/2, goes from rad 3 over 2 to rad 3 over 2. It meets, right? It's a really good kind of thing to look at as you're drawing this out, because I know a lot of you guys are worried about this and holy shit, where does it come together and all that kind of shit. But look at the extremes. Look what happens at the endpoints. See if they meet. That's nice. So one lies on the curve of the other one. That's where it stops. Thank God. Oh man. That's really you need to sketch before you try to start.
Is the limit, I already thought, is y between x with 3 and...
Well, I mean, what does this look like? Well, what is this? Now, I put this here. Is that equal to that? No. No. What does that represent? Does it represent this? It represents the top part because it's positive. Yeah, okay. So I just draw a semicircle. You guys were cool. If it was negative, it would have been the bottom part of the circle. Positive is the upper part of the circle. Right? Now that's what I'm going to draw, but I'm going to draw the upper half. So it's got to go. So let's see. X goes from 0 to 1/2. Y goes from the upper part. From this to that. Let's draw this first. That's the easier one to draw. That's the upper part of this. Wee-haw. Oh, it's close. All right. And then to draw this, I notice that at 0, it's at 0. And at 1/2, it meets this. It makes it so much easier to draw this. So at 1/2, this has got to be on the circle. There is y equals rad 3x. And of course, this is the other one. X squared plus y squared. Rad 1 minus x squared. So where am I going to shade? So as x goes from 0 to 1/2, y goes from this wall to that wall, right? Do you guys see that? So I have to work within here, but y goes from this wall to that wall, this wall to that wall. So this is going to be the region. And even there, it's like awkward because there really is circular region. It's kind of weird to try to draw that. Think x, y with a circular region, but are you guys able to see that pie piece? You don't just have to arbitrarily, I think it's that pie piece. No, I think it's that pie. No, there's no none of that. It's not vague. It has to go from this wall to that wall. That's part of what I try to focus on at the last stuff we did. That's what tells you where to shade. So now I can start to think about polar. What's R going to go from to?
0 to 1.
Yeah, that one's nice. 0 to 1, 0 to 1. So, and of course, theta is going to sweep from what to what?
45.
It's not 45 degrees because that would be y equals x. That's why I wrote this. Yes. 60. Yeah, so it's going to be pi over 3 to pi over 2. Let me stop right there. You have to draw the picture first. Now, you can get a few things from that. But dear God, I would draw that picture first to keep me straight, because then you can think this wall to that wall, that keeps you straight. You shade it in, that keeps you straight. There's so many places to just pick the wrong way. So now, what the hell is this going to look like? Well, the inside's going to be R cosine A. This x has nothing to do with this shit. That's just the function above that region I'm talking about. So sometimes I have people plug some of this stuff in there or whatever. No. That's z equals x. You can't touch that. So x is r cosine theta. And this, of course, this becomes r. I like it. An extra pirate sound or whatever the hell is going to stay in your brain. And then r, of course, we figured out that r goes from 0 to 1, and theta goes from pi over 3, pi over 2. So go ahead and integrate that. Now that we got that set up, this should be the easy part. All right, guys, this is not too bad anyway. You end up with r squared.
Oh.
All right,
I'm on a good track.
that's not a good sound. And when you integrate that, cosine theta being crap at first, we're doing dr, so integral r squared is 1 cube over 3, and cosine theta, and you want to go from 0 to 1, so basically this will just become 1/3, like, just to go straight to the point. And then, of course, the integral of cosine. That's incredible. Of course, remember, the changing gears is weird with the negatives with your trig, so be careful. But cosine does come from positive sine. So it'll be 1/3 sine theta from pi over 3 to pi over 2. At pi over 3, it's square root of 3 over 2. So it'll be square root of 3 over 6. And at pi over 2, it's... I flew it around. I don't know why I did that. So it'll be at pi over 2, it's 1. So it'll be 1/3 minus rad 3 over 6. Cool. Now, I want you to remember, realize that they definitely have some with like squares in there. Good old, remember you have to use the identity, replace that. You should have gotten practice with that from 280. All right, let's do one more of these. Let's do one that's a little bit weirder. Number 17. Were you hoping I was going to do a...
No, I was looking at like the other ones on the bottom.
Oh, okay.
Oh, I didn't know you could pick up.
Ah! So this is a third way they can define our region, right? So we've had two different ways right here that we've done the first two problems. This is a third way they could define it between two given shapes. This is the kind of problem that freaks students out a little bit because you're like, what the shit do I do with this information? So people are thinking.
And this is from 15.3, right?
This is still 15.3, yeah. Yeah, between those two shapes, but they want to be really specific about. So it's inside that circle, but outside the circle at the origin. So nothing about the inner circle, that one in the origin. Well, don't imagine. Practice. Yeah. Trying to do that in your head is not going to get you too far.
So what you graph reference?
No, I'm sorry. Do it. Find the area, the region inside there. Sorry, buddy. I forgot the instructions are at the top, but it's find the area of the region. It's a good question. Didn't have it there up there. Just to make sure everybody's on the right track. That first circle has been moved which way? To the right one. Okay, so it's going to have a center here, and it's going to go. And of course, that other circle is going to be same thing. You center at the origin. So they don't want anything inside this circle, but it has to be inside this one. Outside this one, inside that one. So hopefully it's pretty obvious. It's going to be this region here, which is a funky kind of region. But again, what do I have to focus on now that I know I'm going to do polar interval? I need to know what theta goes from to, what r goes from to. What's this in terms of polar? What's the definition of this circle, this blue circle, in terms of polar coordinates? Who could just tell me that directly?
R squared equals 1.
So then r equals 1. This is the great thing about polar. An equation of a circle should be stupid simple in polar, because that's the whole idea. So I want a 7 radius of 7 circle. It's r equals 7. Bam. So this is r equals 1. What's this dude, though? Oh, shit. Now, why am I doing this? I don't know, Jeff. So I'm converting to polar, but what do I really need to figure out about these two circles that will help me figure out the limits? How am I going to... Where's my theta going to go from to? It depends on where they intersect. So I've got to know that point and that point, so I know what angle is involved, right? Okay, cool. I like it. Don't just guess. It's not necessarily going to be pi over 3 just because it looks big. So I'd rather work with these circles in polar form. That's going to be easier to set up an equation to solve, especially because it's going to actually have an angle in it. All right, so don't set the rectangular equations equal. Oh my God. So this one was x minus 1 squared plus y squared equals 1. So when I convert that over to polar,
R squared minus 2r plus theta plus 1. I got r equals 2.
yeah, r squared minus
2r plus cosine theta
equals 0. Yeah, good. So then you get r equals 2 cosine theta. Cool. And that's just a bunch of plug and shove. And notice, what's the biggest thing on the x-axis for that circle is 2. I mean, you can kind of start to realize anything that looks like a shifted guy, you should be able to figure out it's going to be the furthest it gets times cosine if it's on the x or sine if it's on the y. That's beautiful. All right, and this one was r equals 1, so how do I figure out where they intersect? Yeah, set them equal to each other. Where's 2 cosine theta equal 1? I've got a love that idea. I love that idea. How to find where two things meet? We'll set them equal to each other. Force them to tell you, where do you guys meet? Ah. So then cosine theta is 1/2. Yeah, and my domain or my range from my angle is kind of determined by my picture. So it's going to be negative pi over 3 to pi over 3. Let me do this. He's like, what the hell is that? So R goes from what to what now? What does R go from to? We basically got to stare us in the face. R starts at this wall, and what wall is that? 1. And he goes out to that wall. What wall is that?
2.
It's not 2. It's 2 cosine theta. Be very careful. Right? If it was 2, then it would actually, then it would be a big circle with 0 as the origin, right? So it's not. Yeah, once it's offset, it loses all that nice property stuff. It loses all that easy stuff. So now we got everything we need. So R goes from 1 to 2 cosine theta. Theta goes from negative pi over 3 to pi over 3. What did I put on the inside? I forgot what it was now. Oh, yeah. Well, what did I put on the inside?
It's just 1.
1. Yeah, what's the thickness? I don't want really anything. I just want it to be 1, so the answer comes out numerically to be the same as the area. If I put any function inside, that's like a thickness above this region. So if it's a function that does freaky shit, it's going to be varying thickness, so it's going to actually give you the volume. If it was 7, it would mean that it was 7 thick, so it would be the area here times 7. Right? Because you would just take that number out front, wouldn't you? If it's 7, I'd take the 7 out front. Do you guys see what's happening? So of course, if I want the answer to be numerically equivalent to the area, I want to make the thickness equal to 1. Because what's area times 1? Area. It's crazy. All right. Maybe when you multiply by thickness, you get a volume. So the answer really is a volume, but it's numerically equivalent to the area because the thickness is 1. Yes, sir. Stretching. Okay. I got to figure out a signal you can do. So I do have the R inside there still, though, right? So I'm going to integrate dr is going to become r squared over 2. Pi over 2, Jeff, yeah. R squared over 2 from 1 to 2 cosine theta. So I'm going to get, 4 cosine squared theta over 2, so 2 cosine squared theta minus 1/2. And this will be still from negative pi over 3, pi over 3.
I'm lost on why it's from 1 to 2 cosine theta, not 1 to 2.
Oh, okay. R equals 2 would have to be a circle of radius 2 centered at the origin. That's not what this guy is. What is his definition? R equals 2 cosine theta. How did we do that? We started off with the definition in rectangular. We changed it to polar. So that is the equation. That's the definition of this circle. So from this wall, that's R equals 1. So that's the definition of this circle. To this wall, that's R equals 2 cosine theta. So at 0, it's 2. And at, you can just kind of follow it along. At 90 degrees, it would be 0. I mean, I don't know if you guys should remember having to graph these things. So when it's an offset circle, it can't be R equal to a constant because that would mean it's not offset. R equal to constant is a circle that has origin as a center. I like it. That's why it's not R equals 2. It's got to be R equals whatever its definition is, whatever its equation is. Where am I at? So what do I do with that? That's what I was talking about earlier.
Yeah, cosine squared theta is 1 plus cosine squared theta.
Yeah. Do that.
1 plus cosine.
So remember this, you can always get there. And actually, do you guys remember what cosine 2 theta? Let me just, what was cosine 2 theta? And when I teach this, I try to teach people that cosine is an asshole. He's always first, right? He's sine theta. Sine theta is nice. Sine 2 theta is like, oh, we can both get in there. Sine of A plus B is like, you know, oh, well, let's leave it plus. We'll go together. We'll both take a turn. Sine, cosine. Cosine A plus B is cosine, cosine. Me first. Screw you. And you got a plus in there. I'm going to make it a minus. So I try to. Cosine is a little asshole. So cosine 2 theta. I'm first. Screw you. Cosine squared minus sine squared, and then you might realize that you can make this 1 minus cosine squared, so you actually get 2 cosine squared theta become a squared. Minus 1, which is almost what this is. So you can actually just make this 2 cosine squared theta minus 1 plus a half. You guys see what I'm saying? And it would perfectly match up. So this becomes the integral cosine 2 theta plus a half. We stop. Why is that better?
Because you can integrate it.
Integrating a squared function is always harder than just integrating something with a 2 inside. Who cares? That's linear in theta. Who cares? That's easy. This is not linear shit. Yeah, good. So it'll be 1/2 sine 2 theta plus 1/2 theta from negative pi over 3 to pi over 3. And of course, sine. What's sine of? It's going to be sine of 2 pi over 3. This doesn't really change anything. Yeah. So it's sine of 60 now, right? 2 pi over 3 is going to be sine of 60. That's closer to the y-axis. What's that? Yeah, 60 degrees. 60 degree reference angle, so it's closer to the y-axis, what sine likes. So it's going to be the bigger option. So that'll be rad 3 over 2 over 2. 5 over 6. And then minus, you plug that into this. In fact, this whole thing, well, I don't know if I want to talk about even and odd symmetry and all, but sine of negative 2 pi over 3 is going to be, it's going to be the negative of this, and I'm subtracting it, so I'm going to get 2 of these. And then minus negative pi over 6, so I'm going to get 2 of these, so it's just double that. Oh, shit. So, I want you to realize something. We're not going to make it all the way through 15. Wednesday, we're going to figure out how far we can make it. Wednesday is going to be focused completely on triple integrals. And just because you want more grades, let's have a quiz. Maybe a short little quiz. You want to be able to get it back from me, right? So let's have a quiz just on 14.7 and 15.1 and 2, yeah. 14.7 through 15.2.
Finding critical points and second interval.
Yeah, so finding critical points, I'm going to give you the second derivatives test. And then, like, integration, double integrals over general regions. Try to make it quick. We'll see what happens. Oh, yeah. You are.
Brian.
Okay. Oh, here. Well, this was just this. It's not really complete until I get
Oh, yeah.
that one.
I just wanted my homework for the test I'm going to take this week.
Oh, yeah. Well, didn't agree that. No.
Okay.
Okay.
Let's go.
Oh, good.
Thank you. Do you have